Hi everyone, and welcome to what will be an introductory talk on drift detection. I'm Oliver Cobb. I'm part of the data science team here at Seldon, and in particular I conduct and distill research for our open source Python library, Alibi Detect, which provides implementations of state-of-the-art algorithms for outlier detection, drift detection, and adversarial detection. But this presentation will be focused solely on drift detection. In particular, we'll look at what drift is and why it pays to detector, the different ways in which drift can manifest itself, how drift can be detected in a principled manner, so how we can be sure that any variations or fluctuations are due to systemic change rather than just natural fluctuations, the anatomy of a drift detector, so what specifically as data scientists are referring to by a drift detector, and hopefully along the way, we can demystify some concepts such as online detectors, permutation tests, MMD tests, etc., which, at least in the context of drift detection, are pretty simple and intuitive. Okay, first, to set the scene into which we'll introduce drift detectors. Suppose there's some quantity Y that we'd like to use as part of some decision-making process, be it manual or automated. Sadly, we can't observe Y, but we can instead observe features that are related to Y in some probabilistic manner. So what we instead do is we fit a model to predict Y from the features and use the model prediction in place of the unobservable quantity. The idea here is that we can get an idea of our model's performance or how well we expect it to perform on future data points by looking at how well it performs on held out training instances. So as an example here, we've got a binary classification problem where we're trying to predict a category 0 or 1 given the features x1 and x2. And we fit a model here with the decision boundary shown as the black dotted line. You can see it gets correctly classifies most of the points. To make this a little bit more concrete, we'll think of each data point as representing a person, and x1 representing some indication of economic conservatism, x2 some notion of social conservatism, and the category is representing their voting intention. So here we've got a cluster of economically and socially conservative people who intend to vote conservative, and a cluster of economically and socially liberal people who intend to vote Labour. So a little bit of a simplification, but this is the example we'll roll with. And then given our model can forecast how people intend to vote, we then might wish to use those predictions as part of some targeted ad campaign, for example, where we send people ads depending on which way they swing. And we get an idea of how well we expect our model to perform by looking at how well it performed on held out training instances. And say here, it might be around 95% of the time, for example. But the problem is that's only true assuming that the process underlying the features and the target remains constant over time. And there's various reasons for which that might not necessarily be true in practice and can cause like a degradation in model performance. So that sets up nicely what precisely drift is, which is simply when the process underlying data during deployment differs from the process that generated the training data. And when such a change occurs, we can no longer expect the model's performance during deployment to match that observed on held out training instances. So we're effectively flying blind and we don't know how well our model is performing, which can be potentially dangerous in certain situations. In case you're not particularly bothered about whether or not our targeted ad campaign suffers, I've got an example here from medical imaging where they're trying to predict whether a scan of some sort of tissue is cancerous or not. So they've collected samples from three hospitals here. And their model performs at a particular level. And that comforts them in then using their model on future patients in potentially different hospitals. But the problem is, if in those different hospitals, for some reason, the distribution underlying the images is slightly different in some way. So for example, here, you can see it's slightly different, potentially due to different demographic of patient, or potentially just like a different stain used on the slide, on the microscope used to take the scans. then we can no longer be sure that the model can handle this slightly changed data distribution, and the model then might misclassify whether or not the tissue is cancerous or not, which clearly isn't ideal. And yeah, by the process underlying the features and the target, what we're really referring to is this joint probability distribution. And the different types of drift correspond to different changes within that joint distribution. We now return to the voting intention example, which is slightly easier to illustrate concepts with. And just a reminder, this is what the undrifted data distribution looks like. So one type of drift that can occur is concept drift, where it's the relationship between the target and the features that changes. So suppose for some reason, perhaps due to a new tax policy, for example, people no longer intended to vote along economic lines, but people intended to vote solely along social lines. Then suddenly our model is misclassifying a lot more points in these sort of areas where, so for example, on the sort of economically conservative but socially liberal people and the socially conservative but economically liberal people, our model is getting the wrong predictions, and resultingly the model performance will suffer. An alternative type of drift that can occur is this sort of a prior probability drift, where just the proportions of Conservative or Labour voters has for some reason changed. So here, for some reason, clearly a far higher proportion of people are now Conservative for whatever reason. And now the model would have been better off shifting its decision boundary, because the points around the previous decision boundary are now overwhelmingly Conservatives. So again, the model performance has suffered. An alternative, but quite similar type of drift that can occur is this covariate drift. So suppose, for example, that for some reason society becomes more divided and people are pushed towards economic and social extremes, then in this context, the model performance might actually improve, because there's sort of less people falling into this region on which the model is uncertain. It's actually become an easier problem for our model to deal with. But instead, suppose that society comes together for whatever reason, suddenly it's more like one big cluster and there's more people falling into the region on which the model is uncertain. Clearly, the model is now misclassifying far more people here than it did here, and the model performance is going to decrease. You might be thinking, oh, this seems like so when the model performance decreases, we refer to that as a malicious type of drift. It's a change in the distribution that has caused our model performance to degrade. And you might be thinking, oh, it seems straightforward enough to detect when this occurs. We can just monitor the performance of our model, evaluate the model loss continuously. And when it decreases, we know that there's been some sort of malicious drift. And indeed, that's sort of how supervised drift detection works. We model the model performance directly. But in reality, what we actually observe during deployment looks a bit more like this. We do not observe the model labels. And this makes certain types of drift much trickier to detect. For example, this concept drift suddenly is no longer observable when we don't observe the labels, because the distribution of the features has remained the same. And therefore, we're forced to look for changes directly in the distribution of the features. And that's much more challenging, because the features are often very high dimensional and complex. For example, they might be images or text. So whereas here, it kind of seems easy enough to sort of eyeball this two-dimensional problem and say, oh, clearly that's not quite the same distribution as this. There's been some sort of drift. Can't trust our model performance. But when in reality we have collections of images, that's a much trickier problem. And this problem, where we're forced to look directly at the features, is then unsupervised drift detection, which is pretty similar to the sort of traditional problem of change detection. Okay, so given that we observe some sort of change in the features, it remains to determine what exactly it means to detect drift. Because, for example, This looks pretty similar to the undrifted data. If we looked at that, we probably wouldn't say, oh, there's been drift. But if we look at this, suddenly like the clusters look a little bit closer together. But it's not clear whether that could have been just due to like a natural fluctuation with the underlying process remaining the same, or whether there has been some sort of like systemic change. Here, clearly the distribution has changed. We've now got this sort of like central cluster, and we'd probably be quite confident in this case flagging drift. But the problem is, where do we make the cutoff? How much change do we need before we say, oh, there's been drift and we should take corrective action? The way that we can do this in a principled manner is via statistical hypothesis testing, which I'll now quickly overview for those of you who didn't do stats at school or are desperately trying to forget the experience. It works by, prior to observing the data, specifying a null and alternative hypothesis, and also specifying a test statistic, which is a function of the data that we expect to be small under the null hypothesis and large under the alternative hypothesis. Then we observe the data, compute the actual observed value for the test statistic, and the associated p-value, which is the probability that such an extreme value of the test statistic would have been observed under the null hypothesis. The idea here is that a low p-value, so a very unlikely event, sort of discredits the null hypothesis. It's like saying we could continue to believe the null hypothesis, but we'd have to also believe that we just happen to observe some extremely unlikely data. And so the way it typically works is that we specify a threshold on a sort of false positive rate, below which, if the p-value falls below that threshold, we then reject the null hypothesis. And the way this works is that even if the null hypothesis is true, the p-value will be below the threshold p% of the time. But at least now we know exactly how often that is, and we can flag drift in a principled manner, knowing how likely the detection is to be false. So yeah, in the context of drift detection, with Q0 representing the distribution underlying the training data, and Q1 that underlying the deployment data, we let the null hypothesis be that the two distributions are the same, and the alternative hypothesis be that they're different in some way. And then we do our best to specify a test statistic that we expect to be small if the distributions are the same, and large if the distributions are different. Then we compute the p-value and flag drift if it's below some threshold that we specify to correspond to some false positive rate. But this is the hard part. Specifying a test statistic, so a function of potentially a big sample of images or text that we expect to be small under no change, large under change. And even if we are able to do that, how do we then associate it with a p-value and say exactly how likely it was to have observed such an extreme value? This is a difficult problem. But lest you think it's not difficult enough, we don't actually, in practice, observe all of the deployment data as one big batch that we can compare against the training data set. What actually happens is we observe it sequentially over time. What we'd like to do is to detect drift as soon as possible after it occurs. So using as few of these data points as possible, so that we can limit the amount of damage that might be caused by a low-performing model, for example. And so the sort of framework that we set up for this is that we assume the data points follow the training data distribution up until some change point t star, and then thereafter it follows some alternative distribution, which is no longer the same. And as each point arrives, we perform a hypothesis test of whether or not there is evidence that drift has already occurred. And yes, this whole problem is referred to as sort of online drift detection or sequential drift detection, as opposed to offline, where we consider big batches at a time. And so in designing sort of online drift detection algorithms, there's sort of various properties we might wish to consider. The first is that we'd like the algorithm to be fast to respond when change occurs. So we consider this quantity the expected detection delay, which is the difference between the time at which we detect change or drift, t dash, and the time at which it occurred, t star. We'd like that to be small in expectation. But we'd only like it to be small subject to a known frequency of false detections when there's no change. So we call this the expected runtime, which is how long we expect our algorithm to run in the absence of change. So we can think of the change point being at infinity, it never occurs. And yeah, we'd not only like this to be low, but we'd like to know exactly what value it takes so that we can respond appropriately when a detection arises. Because, for example, if detections occur every, say, 100 instances in the absence of change, we're going to respond entirely differently to a detection to if it occurred every 5 million instances. So just specifying a sort of lower bound on the expected runtime isn't particularly useful because there can still be orders of magnitude difference, and we're not sure how significant a detection is. But other than that, you might have noticed that there's sort of this inherent trade-off between the expected runtime and the expected delay. So we'd like the expected runtime to be large in the absence of change, but that requires a detector which isn't particularly sensitive and likely to give false alarms, whereas we'd like the expected delay to be small, but that requires sensitivity. So it's very difficult to get both. Yeah. Yeah, and as I say, this point is often overlooked, designing algorithms such that the frequency of false detections is known, and that's important in order to respond appropriately. Okay, so for this problem of sequential change detection, detectors can be usefully categorized by how they window the data. So by that, I mean, so if we consider data arriving sequentially, so time steps 1, 2, 3, 4, etc. These are the features plotted here. There's various ways that we can window this data. The one way is using disjoint windows, where, for example, the first window would be the first 5 data points. Typically, it'd be much larger than 5, say 500, but for illustrative purposes, we consider 5. We perform a test. If we get a p-value of below some threshold, we flag drift. If not, we move on to the next window, which contains none of the same instances. They're disjoint windows. We perform a test, and the window progresses like that. An alternative way is using overlapping windows, where again, we have a fixed size window, starts with the first 5 instances, do a test, p-value, etc. And then we slide it along by just a single instance, and we perform another test. So now we're performing a test every time step. And the window progresses. Third way is with adaptive windows. And algorithms using adaptive windows often don't sort of formulate them as windowing approaches. Typically, you accumulate some you have like a test statistic trajectory that you monitor for changes, but they can be thought of in this sort of adaptive window approach, where you start with a window size of 1. Not only do you perform a test, but you consider whether or not you'd like to allow the window to grow. So if, for example, there was no evidence at all for any sort of change, you might just say there's no point in the data point, it's not useful for detecting change, and move on to the next. Then suppose you have a data point that is indicative of change, but not so much so that it results in a p-value below the threshold. You might then allow the window to grow. And again, a bit more evidence for change. You allow it to grow and you allow the evidence to accumulate, which is like particularly useful when drift is quite slight. And you have this sort of like forgetting mechanism such that if at some point you decide the window doesn't contain evidence for drift, it then resets back to 0. So yeah, you've got these different windowing strategies. They all call for different sort of test statistics and mechanisms for determining the significance of the test statistics. And they all have their own pros and cons, which we'll dive into a little now. So firstly, the disjoint window detectors. So this is the strategy adopted by most existing detectors in Alibi Detect. And it is a bit of a sort of offline detection approach where you consider big batches at a time, where you can sort of apply it to the sequential drift detection problem that we just considered in the way that we just considered. And the key strength, one of the key strengths of disjoint window detectors is that we can use any test statistic and compute a corresponding p-value using what is called a permutation test. The permutation test is actually dead intuitive, so I'm just going to quickly overview exactly how that works and how you can determine exactly how extreme any given value for the test statistic is. So we have our window of training data, we have our window of deployment data, and suppose we have some way of shuffling these windows such that the shuffled training window has training and deployment instances, the shuffled deployment window has training and deployment instances. What we do is we compute the test statistic on a large number of shuffled windows. So we suppose B is a large value, and we compute a large number of shuffled test statistic values. And then what we do is we compare the test statistic on the unshuffled windows to a test statistic on the shuffled windows. And the idea is that if there hasn't been a change, they all follow exactly the same distribution. So we don't expect that the unshuffled version would fall in, for example, the top 1% of the values, because that would only happen 1% of the time. So that gives you the p-value. So yeah, if say the top X%, the unshuffled value is in the top X%, that X then forms your p-value. And you know exactly how extreme it is by how, towards which end of the spectrum the unshuffled value occurs. Yeah, not only are we able to compute the p-value for any test statistic, this test statistic can also be different between windows, which is really useful because it allows us to learn a new test statistic for each window. So typically these windows are quite large, and we can use a portion of the data to learn the test statistic which is sensitive to sort of change that is present in the window. And then, so you can sort of automate the construction of the test statistic and completely get around the problem of not knowing how to specify it. And that's really useful. Yeah. The problem is using disjoint window detectors in this manner, they're quite sensitive to the window size, because if you use too small windows, there's not going to be enough data there to obtain significant test results, and you probably won't detect a drift that might have occurred, particularly if it's slight. But if you use a really large window size, suddenly you're only testing every, say, 500 or 1,000 instances. And even if really severe drift occurs, you're unable to detect it until the next test point, which might be a large number of time steps away. So the expected delay is large, and there's no way around that, really. Alternative is to use these overlapping window detectors, and these use test statistics that are updated incrementally, which is important because we're performing a test at every time step. So it's important that that's not an expensive procedure and that we can do it in this incremental manner. Sadly, configuring overlapping window detectors to operate at a specified expected runtime is much more difficult because of the correlation between consecutive test outcomes. So, for example, if the first window of data, if we don't detect drift on that window, suddenly the next window of data, which contains much the same data points, is also much less likely to have drifted. We have this sort of like correlation between test outcomes, which means the relationship between the expected runtime and the p-values is pretty much completely undefined. And this is something that I've been working on, how we can configure detectors to target a given expected runtime. And it turns out you can do it using any test statistic that you like. However, unlike the disjoint window approach, it must be pre-specified. So we can't learn a test statistic for each new window. And therefore, we still have this problem of specifying a test statistic, which is small under no change, large under change. However, if we are able to specify such a test statistic, relative to disjoint windows, they're computationally light because of the incremental manner in which they operate, and they're fast to respond to severe drift, because when severe drift occurs, the severely drifted data points are in the windows straight away, affecting test outcomes, and therefore we're faster to respond to them. So we sort of have this trade-off where the test statistic might not quite be as suitable, but it's being influenced straight away, so potentially it's actually faster to respond. The third strategy is these adaptive window approaches, which typically accumulate some notion of outlierness. At least that's the approach taken by methods that have a sort of fixed cost as time progresses and for which the post-change distribution is unknown. So how it works is that the sort of test statistic is evaluated on each data point in isolation that arrived, and it has a negative expected value under no change. So the sort of, as we accumulate these values, the trajectory goes down, and it has a positive expected value under change. So once there's been a change, the trajectory starts to go up. And we sort of specify this threshold, some threshold for how much the trajectory has to increase by for drift to be detected. That's the challenge, is to know how to set this threshold to target a given expected runtime. This is something I've also tried working on, but it actually turns out that this idea of accumulating outlierness is not necessarily great for drift detection for reasons we now consider, because originally it was like kind of surprising to me. I thought this was quite an intuitive way to detect change, because if the distributions change, the points will appear more outlying. And therefore, if we accumulate some notion of outlierness, it'll go beyond some threshold. But it actually doesn't work for reasons we now look at. So if you consider the training data distribution to be this sort of two-dimensional isotropic Gaussian, so with the bright color in the middle representing region of high probability, darker as you get further away, representing regions of lower probability, and pink points representing the training data set or training window. And then suppose during deployment, we observe these 7 points from what is clearly a different distribution that's much more tightly clustered, so lower variance and also a different mean. And if we're accumulating a notion of outlierness, the problem is that none of these points in isolation are particularly outlying, because that's determined by how far they are from the center, and they're not super far. So those data points, considered in isolation, are no less likely than, say, these data points, which we wouldn't have looked at and said that there's been drift. So as we might have looked at these and said, oh, that looks drifted. We wouldn't have done so with those, but they're treated exactly the same. So that's kind of the reason why accumulating outlierness doesn't necessarily result in great performance with respects to delays. So if accumulating outlierness isn't a great way to specify test statistics, what is? It turns out those that estimate some notion of distance between the distributions, which hopefully that should be kind of obvious by now. And one way to achieve this would potentially be by estimating distributions separately and then evaluating some notion of distance between these sort of models of the distributions. But given very limited samples, it's usually more efficient to try and directly estimate the distance. The one particularly common way of doing this, which features prominently amongst our Alibi Detect detectors, is using what's called the maximum mean discrepancy, which probably seems pretty obscure to people, but it's actually pretty intuitive. So we're just going to quickly look at how that works now. So maximum mean discrepancy, which you see has this sort of like subscript K, which refers to a kernel, which is sort of a similarity measure between data points rather than distributions. So whereas we're looking to define a distance between different distributions, MMD transforms that problem to merely specifying a similarity between points. And that's much simpler and possible to do across different data modalities, be it text, images, graphs, etc. Typically, how it works is by defining some projection of the data into some Euclidean space and performing an inner product, sort of looking at how much in the same direction the projections are. So for example, for images, we could use a pre-trained ConvNet to project the images onto say a 64 128 dimensional vector, or similarly for text, we could use a transformer, etc. And then what the MMD does is it uses this notion of similarity, and it looks at the similarity between the data points in the training set. It looks at the similarity between the points in the deployment window. And then it looks at the similarity, like the sort of cross similarity between the training set and the deployment window. Often you'll see it written like this, which is a little bit more intimidating, but just think of these average similarities and cross similarities. The idea is that if there's been a change, then the similarity between the deployment instances will be different to the similarity between the training instances. So for example, suppose this is a similarity between the training instances, and relatively this is quite small relative to the similarity between the deployment instances, and these are all very similar. And then these cross similarities are also pretty small. They're not particularly similar. So what the MMD does, it says, well, so we've got a small similarity between training instances, add it to a large similarity between deployment instances, and take away 2 times the small similarity, cross similarities. So we have sort of small plus large minus small equals large. It results in a large distance because of the differences between training and deployment. But if there hadn't been a change, for example, actually no, so once we've computed this value of the MMD, so how different the distributions are, how do we associate that value with a p-value that says exactly how extreme it is? So 0.7 seems maybe quite large, but how extreme is that? We can determine that using the permutation tests I described before. So here, we now consider shuffled training windows and shuffled deployment windows. So we've got a mix of training and deployment data in both. And the similarity is low in the training window, the shuffled training window. It's low in the shuffled deployment window. It's low between, and low plus low minus 2 times low. They all cancel out. Basically, all of these are expected to cancel out if there hasn't been a change. And the MMD is small. So the idea is that when there's been a change, this is large, all of the shuffled values will be small. And therefore, the unshuffled value will be in the, say, top 1% of all the shuffled values. And we say, okay, well, in that case, the p-value is 0.01. That would only happen 1% of the time if there hadn't been a change. Okay, and that's pretty much it. So when I think of a change detector, drift detector, I sort of think of this box with a smiley face and know that there's 3 main components: a windowing strategy, a test statistic that defines the notion of distance between the deployment window and the training window. And this might involve some sort of projection and MMD, as I showed before. And then we have some sort of mechanism for determining precisely how extreme any observed value of the test statistics are. And then additionally, we have a sort of we can specify the expected runtimes. This is a sort of dial that we can turn. And as we do that, under the hood, the expected detection delay will be changing, but that's not what we directly manipulate. We choose the expected runtime so that we know how to respond to detections when they arise, because we know how significant they are. So just as a sort of final example that's slightly more realistic than the voting intention example, suppose we have some sort of application requiring some facial recognition component, and it was trained on this distribution represented by these images. This is our training data distribution. But then during deployment, the distribution changes somewhat. We now have a far more diverse demographic using the application. And that, when this occurs, the model is likely, the facial recognition model performance is likely to degrade, and we need to be able to detect it. So how can we go about doing that? So we specify a test statistic using the MMD. There's a notion of similarity between data points. We use a pre-trained convnet to project the images onto vectors, then we take their inner product, and that defines a notion of similarity. We've used disjoint windows, and we obtain p-values using permutation tests in the manner I described before. And when these p-values are below some pre-specified values that correspond to our desired runtime, we flag drift. And we know how to respond because we know how significant it is. And that's pretty much it. So thank you for watching. As I said at the start, we have a sort of open source Python library that has implementations for a lot of state-of-the-art drift detection approaches. So for example, we have those based on maximum mean discrepancy, as we discussed. We have these sort of classifier-based approaches that learn the test statistics using a portion of the data, as I also discussed. We have detectors that look at drift into and out of areas of model performance, which are designed to be particularly sensitive to drift that's likely to be malicious, which is particularly useful. And yeah, we've recently integrated some online detectors as well. So yeah, do check it out. And I hope you find this presentation useful. Thanks a lot.